Everyone for being here today. Welcome to Pivvot's webinar, The Power of Data in Large-Scale Geospatial Problem Solving. My name is Abby Sawyer. I work closely with Pivvot on sales and marketing, and I'll be moderating today's webinar. Today's speakers are Justin Calvert, Director of Software Engineering, and John Salva, Manager of Data Architecture. Justin has over a decade of experience and specializes in the intersection of software development and geographic information systems. Justin plays a crucial role in spearheading our cutting-edge software solutions here at Pivvot. John is a certified data management professional. He has over 10 years of experience in data management and geospatial analysis. So just a few quick housekeeping items before we get into our presentation here. The chat is closed, so any questions you have should be submitted through the Q&A button at the bottom of your screen. Feel free to submit questions throughout the presentation, and we'll have time at the end for Q&A where we'll address any questions that have come in. If you don't have any questions, we'll follow up with you later if you think of anything. Additionally, if we don't get to your question, we'll follow up with you via email, so feel free to ask away. With that, thank you everybody for being here today, and I'll pass it over to Justin to kick us off.
Great. Thanks, Abby. I am going to start with a brief overview of what Pivot is, but before we get into that, I want to start with an IIF moment. IIF stands for Incident and Injury Free and is part of Terracon's safety culture and make sure that we all are aware of our day-to-day activities and that we're taking the safety culture home with us. My IIF moment today relates to school. School starting back up, and that means an increase in activity. That increase in activity is both in children and kids waiting for the bus, running through a parking lot, heading off to school, and also traffic. So just be aware that school's spinning back up. There's a lot of folks out there with school-aged children that are excited to get back in the classroom. And probably the best way to account for the increase in activity is to make sure that you give yourself enough time to get out the door and safely travel to your location, your school, your job, whatever it may be. If you have school-aged children, that could be difficult, but do your best and just be aware that it's more important to get to school safely than it is to get there on time. But that all traces back to making sure that you give yourself enough time to travel to your location. So with that, we'll roll into what is Pivot. And I'm going to keep this very brief. I think there's a lot of folks on this webinar that are aware of Pivot and its capabilities. But for those of you that are new, you should know that Pivot is a cloud-based platform that aggregates industry standard data from various verified sources and offers tools to assist with project planning and decision making. The platform provides features for analyzing data to identify opportunities and constraints, supporting planning throughout a project's lifecycle. We provide our solution through a number of tools or applications inside of the platform. Aware is the entry point into the Pivot ecosystem. Aware provides access to our data and reporting in a very easy to access format. You can report directly on Pivot data, bring your own data, or merge those data together and produce quick insights on specific spatial locations. In addition to Aware, we provide more in-depth tooling that answers deeper business-related questions. Routing and siting are two of our applications that are focused on specific workflows. Siting looks at specific locations related to tax map parcels or landowners and allows you to derive deep insights on the underlying information about that site. Routing provides a linear corridor analysis and munges all of the Pivot data together to produce deep insights into a linear corridor. Think pipeline, transmission power line. All of these applications are powered by Pivot data. Pivot data is the backbone of our system. And while John will be talking about it more today, I think it's worth noting that Pivot data is provided within the Pivot platform, and it is an aggregate of data that is curated and updated on a regular basis by John and the rest of his data team. They do a great job of providing the foundation for the power of the Pivot platform. With that, I will hand it off to John to tell us more about what you can do with Pivot data.
Awesome. Thanks, Justin. All right. So the topic of this presentation is the power of data in large-scale geospatial problem solving. So let's start with the problem. It's going to be a made-up problem. The what of this problem is not important, but the how is what I want to focus on. So we're going to present the problem of we want to build a widget factory. Where do we build it? And we're going to walk through sort of Pivot's methodology and some of the data sets we could use to answer this question. If you have any actual examples, any whats that you would like to share, please throw them in the chat box or the question box rather, and we can discuss those after the presentation during the Q&A session. All right, so our goal: where to build a widget factory. One of the first things we need to identify is what is the scale of the problem we're solving. Finding a place for a widget factory in Clark County, in a single county, is fairly straightforward. Let's scale that up and say we want to look for a place or places. Maybe we want to build an army of factories. Where in the U.S.? We want to scan the entire U.S. for some good areas to build our factories. So I'm going to frame this this example as a choose your own adventure book. If you might remember, in the 80s or 90s in the elementary school libraries, choose your own adventure books where you open it, read the intro, learn about your hero, and then you come upon a decision. Maybe you can head towards the castle or go into the cave. And if you go into the castle, you flip to page 27 and find out what happens. Or if you go in the cave, you flip to page 58 and find out what happens. So we're going to walk down that path. Whenever there is a choice point, I've indicated that with the exclamation symbol there you see in the lower right, to kind of call attention to we're making a decision that's going to affect our analysis at this point. Sort of the roadmap in front of us, we're going to select our data sets. We're going to determine our analysis format, determine the resolution for that analysis, identify appropriate parameters for that analysis, and then iterate on our solution and then scale our solution. Okay, so first question that we need to answer, first choice point is how do we want to visualize our report or our results? What is the end goal? And for this, we're going to draw inspiration from this NOAA heat map. This one happens to be a literal heat map. It shows high temperatures across the nation. But could we do a similar map? Show good places to build a factory in green and bad places in red to help us make our decision. So we'll use this. Keep this in mind as sort of a starting point, and we'll see where we end up. The next major choice is what data are we bringing? And there's kind of three ways we think about data. There's industry standard data, which Pivot curates a large collection of, as Justin mentioned. There's project-specific data. So this is stuff that is going to be either proprietary or bespoke to a particular project or problem. It might not be cross-applicable. And then also expertise. So may or may not be data itself, but the lens through which we look at that data and discuss it. So Pivot curates, their large catalog, which we talked about. That sort of covers most of the industry standard data. You could bring your own data. That is where most of project-specific data is going to be coming from, as well as maybe some industry standard data that Pivot doesn't yet curate. And then for expertise, our parent company, Terracon, we collaborate with them weekly, if not daily. They have a huge amassing of very smart geotechnical and environmental practitioners that we lean on a lot to validate sort of our analysis, what we're doing, and make sure it makes sense for the actual result we're getting. So our selection for this example, we are going to just look at 3 sort of data sets that Pivot has in our industry standard data sets, just to keep things simple. Our first data set is commercially navigable waterway in our hydrology data collection. And we're using this because we want a way to distribute widgets, maybe import pieces of the factory via those waterways. So use that as our transportation method. So we want to be relatively close to commercially navigable waterways. We want proximity to power. We need that access to power for the machines that are going to make these widgets. And for that, we're going to lean on our electric transmission power line and substation data sets. And finally, depth to bedrock. We need to make sure the ground is suitable for building our widget factory. And so for that, we're going to use GSurgo depth to bedrock data set coming from NRCS and curated by Pivot. So after we've identified what data sets we want to use, we need to be a little bit more specific in how we are going to use these data sets. And I'll pause here for a moment because the data set selection portion is probably the most crucial point in this. Everything after this can be tweaked and ran, but we really want to hone in and make sure our data sets are solid and we know what we're using, what assumptions we're making at the top. It's going to save us a lot of time down the road, which I'll talk about a little later. And I say that because our parameters here are less stringent up front. By the time we solve our whole problem, we want to have these dialed in, but we can make some assumptions and know we're going to change them later. So just to start, we're going to say let's do 5 miles. We want our area of interest to be within 5 miles of a commercially navigable waterway. So there's not a lot of extra transportation across land. We want our proximity to power to be within 5 miles. We don't want a lot of costs associated with building out and connecting to the existing infrastructure. And for bedrock, we want to avoid things, bedrock less than 4 feet, greater than 4 feet, or greater than 6 feet rather, we'll prefer, and anything in the middle we'll deem acceptable. So after we've selected our initial parameters, we need to choose an analysis unit, how we're going to look at this data. The first one that often comes to mind is ownership or jurisdiction, and I'm kind of throwing anything in this category, any sort of man-made boundaries. So this could be as small as property parcels, individual units of ownership. This could be census or other data collection or voting blocks, things like that, county boundaries, state boundaries, all the way up, right? The problem with these often is they're inconsistently sized. They do have meaning embedded within them beyond their shape, like ownership information, which can be valuable for certain analysis. But if you're just looking for a unit, they're not often preferable because they're not equal to one another. They also can change over time. It's no surprise that property parcels can change frequently as land is bought, sold, and merged. But even things that are seemingly static, like county boundaries, do change. I believe a few years ago, Connecticut, for example, just redrew all their county boundaries, and voting boundaries can change more frequently than that. Another issue with them, other than their irregularity, is that there are potential gaps and overlaps with them. So in this example here, this shady trail running through this property parcel example, that is actually not covered by a polygon. May or may not be a problem for our analysis, but it is not complete coverage. You can also have, municipalities or cities that can cross municipality lines. So there are gaps and overlaps sometimes inherent with these man-made drawn boundaries. So unless there is a good reason for that, unless you're interested with some of that information that is embedded with those shapes, we tend to avoid that. Another option we have for our units is quad key. So this is a hierarchical structure. You see level 1 there, it divides the globe up into 4 quadrants, and then it goes all the way down to level 3, dividing each subsequent level into four blocks. This is very scalable. If you make an analysis at level 23 and you maybe want to roll that up to a higher scale, say level 13, you can easily do that and sort of aggregate and do analysis that way. It's a good way to reduce bias, right? These squares, these units are all equal size. They do not represent boundaries. So it's a more fair, less biased way of doing analysis. You can also, once you've moved your data into this quad key format, it's easy to compare it against any other data set in quad key. So it's a good way of kind of making data speak a common language, bringing multiple data sets together to speak a common language and quickly analyze them. Another system very similar to quad key is HexGrid. This is what Uber uses, Uber H3 uses for their rideshare program, right? So hexagons identifying, where a person is standing on a street corner and able to locate their vehicles and route to them. This shares a lot of the benefits with the quad key method, but it's even more fair, I'm calling it, because as you can see in the image below, how the shapes tessellate, when you tessellate triangles or squares, the shape that is to the left, right, up, or below it in the example of a square, the distance from the centroid of the center square to its neighbor is shorter than the distance from the center square to its diagonal neighbor. So that they don't tessellate equally. Whereas hexagons, if you start in the center, the distance to a center point of any of its neighbors is the same. They're all equidistant because of how they match up on the sides rather than on the sides and corners. So for those reasons, we're going to choose the hex analysis unit for our example. Bedrock and commercial navigable waterways do not respect human boundaries. They're natural phenomena. Jurisdiction is not a concern in this analysis. Power lines are man-made, but for this, we're not worried about who or why they were built, and we're not worried about ones built in the future. We just are worried about where they exist currently. So that's just a fact of where they exist. And we want a fairly and evenly distributed analysis as well as continuous coverage, which this hex method provides us. So we've decided we like hexagons. Now we need to decide what size hexagons we're worried about. Just for example purposes, I'm going to pop back over to the world of man-made boundaries. So for jurisdictional boundaries, often what we look at when we're talking about resolution is we start at the national scale, then go down to regions, states, census tracts, census blocks, all the way down to individual parcels. So you can kind of get an idea as we're moving from very broad things to very specific things. The hex grid kind of has a similar distribution. So there's resolution 0 at the very top, which has hexes with a size of about, exactly 1,281 kilometers. So we'll look at what that means practically using a map for some example here. So just to illustrate this, I've selected a point of reference, just a random house. Everyone kind of has a size in mind of what a house and the surrounding yard looks like. This is what a level 15 hexagon grid looks like applied to that area. So as you can see, it's quite dense. There's a single hex, so you can kind of see how big one is without all the noise of the complete grid. Zoomed in a little bit, so you can tell it's an actual hexagon, not a point. So that's about, half a meter, 2 feet. So we're talking about, a single human standing on a piece of land. Really good for Uber rideshare if you're trying to find a person standing on a street corner. Probably overkill for the analysis we're wanting to do. On the flip side of that, level 0 is probably too general. So these are the biggest hexes that this system provides. Our dot, our example point is right there, and you can see this whole this hex covers the complete gulf here. Again, there's that 1,281 kilometers for the side of the hex, so that's too big. Level 10 is a pretty reasonable size, about 75 meters per edge, covers about that house and its surrounding lawn. So a good size for the scale of analysis that we want to do. So there's that same image with the whole grid drawn in. Small enough to assess our use case and pull out some meaningful results, but it's large enough to process efficiently. You might say, well, sure, 15 might be overkill, but why don't we just do it and get the best results? Well, there is cost associated with processing as you go up and down, right? The more units you're analyzing, the more machine costs that you have to throw at it. And going from a level 10 to 15 is what, 16,800 more hexes. So every time you move down a level, you're adding 7 hexes per unit, because there are 7 hexes that make up this large one. So it quickly can get out of hand if you go too small. So you want to find that sweet spot where you're getting valuable results, but as big as you can to save on cost. All right, so we've made all our initial selections. All the choices are on our choose your own adventure. So let's run this and see what we see. So we're going to select a single county to run it. We don't want to execute it on the whole country yet. So I just chose Wilcox County in Alabama, just randomly for an example. You can see our distribution there. We have some nice dark green areas that meet our conditions. Kind of a zoomed in shows the individual hexes representing different values of prefer and avoid. And this analysis took about 2 minutes to calculate. Once we made all the decisions, got all our data arranged, and plugged everything in. So not too bad. But we don't want to stop there. Let's iterate on this process. Going back to our choose your own adventure example, if your character fails their quest in the book, or you reach an ending that you don't like, you can flip back a few pages in the book and maybe make a new decision and see if you like that one better. So that's what we're talking about here. And another thing to keep in mind is the level at which you make that change. So we would rather fail, or we would rather fail 2 pages in, and flip back a few pages rather than 50 pages in and have to trace back. Oh, well, I went to page 27 and then I went to page 13 and then I went to page 84. Trace all the way back. It's better to solve, correct any problems as far upstream as possible. To prevent wasted time, wasted cycles downstream. So where we are right now is the perfect time to iterate. We have all our data sets locked in, but we can maybe fiddle with the parameters a little bit. So this is the same slide I showed before with our end results. Again, the 2-minute compute time for this county. But I've thrown our parameters up there for a reminder. So we have 5 miles to waterways, 5 miles to power, and we want to avoid the less than 4 feet bedrock. So we did this and it looks great, but we used some of that expertise I talked about and talked to one of our geotechs, and for this they say, hey, you got this completely backwards. We actually want the shallow bedrock. Maybe we have something we need to embed in it. Again, don't hold to the what too strongly, just using this for an example, but we made a mistake here. So let's flip this on its head. We actually want to prefer the shallow bedrock and avoid the deep bedrock, and we'll leave the 4 to 6 acceptable in the middle. And so that completely flips our analysis, right? Now we're starting to hone in on some really good green areas here with that bedrock power and waterway conditions met. And that switch in analysis only took about 2 minutes, right, to make that change. So we've decided, okay, that looks good. Can we be even more stringent in our proximity to power? 5 miles is great, but if we can get within 2 miles and worry less, maybe we can save even more that cost to build out the infrastructure to connect into what's already there. That would be great. So let's tighten that a little bit. And so if I toggle back and forth between these, they look very, very similar, but the corridors there kind of squish down. So we're honing in even more on what we want. And again, this iteration about 2 minutes. So now that we've seen what this actually looks like and we are getting some good results that meet all our conditions, let's like turn this up to 11, right? Let's just eliminate everything that's outside of our commercially navigable waterway. Let's say that's a deal breaker now. That's not just we want it close, it has to be close. So we'll just completely eliminate everything outside of 5 miles from commercially navigable waterway, and we get something like this. So some very keyed in results, areas that we want to focus on. And this is great because these are 2 minutes. So what, I'm up to 6 or 8 minutes. How many times I've iterated over this? You can sit down in a meeting and hash this out once you've got everything set up. Get an expert in there, get a business person in there, get a data analyst in there, look at all these things and iterate over these and ask questions and see what kind of results we get back over the course of a half-hour meeting. Rather than sending emails back and forth. It's a very efficient way to work. Okay, so we're good with that. We're going to lock in those parameters. Let's go ahead and run it for the entire state, and let's just see what this looks like. I ran it twice here just for visual purposes. One without the commercial navigable waterway elimination criteria on the left, just so you can kind of see the plot of the entire state. And then the one on the right is with our totally dialed in parameters where we do eliminate all the outside of 5 miles from navigable waterway. And you start to see, some really good areas. Just looking at this at a glance, it looks like the center of the state right there is a really good place. Lots of good options to focus our attention. Not so much down here towards the bottom. There are also some options up here, but we're really dense in our good meeting of criteria in the middle. And all told, that took about 1 hour and 11 minutes to run for the state. So again, you see, you probably wouldn't want to run the state in the confines of a meeting. So dial it in at the county level or equivalent-ish, and then start to scale once you're locked in with some of these decisions. So before we run it for the entire country, I noticed something while I was playing around with this, right? The commercially navigable waterway data set, it doesn't touch all the states in the country. Here, I'm showing a map of the country with all counties highlighted that interact with the commercially navigable waterway in some way. So, 900 counties out of 3,000 for the total counties in the 48 states. That's about a 30% coverage by count, by number of counties, and only a 25% coverage by actual area of land. So here's a huge savings that we could make right here. We don't even need to run, analysis in Arizona or New Mexico. We can just rule those out, put a big black square over those. We only need to focus on these ones where we have commercially navigable waterway because we've already ruled out all that other stuff. So here, not even doing any processing. By doing that upfront iteration and keying in on what we really want, now when we're scaling to the state and entire country level, there's a huge cost savings we're able to realize here. So I'm going to go ahead and run this for the entire country, and you can see what our results look like here. Now, I cheated a little bit, and this is sort of in the spirit of cost savings, right? I ran this at a level 7 because I was running it at the entire country, and I just wanted a nice visual for this presentation. You can see here, even a level 7, I cannot on this image see an individual hex, right? It's too small. So maybe if you were running the entire country, you could add another level of iteration there where we run it at a level 8 or a level 7, hone in on some areas, and then maybe rerun it at a level 10. Or if we wanted to get even smaller, a 9 or an 8, get smaller once we start to zone in on our areas. Only use those small hexes when needed. But this is still a valuable slide. Again, at a glance, there's some really good areas. I see a lot of green over here, kind of in West Virginia. Still some down here, which we saw in our single state analysis. There's also maybe some options over here in California. So you can get an idea and start to hone in on areas you want to focus on closer. So we've done all this good analysis. We have our results. What are some mechanisms for delivery, that we could give it to someone to continue and take actions on it? Very straightforward way of delivering this is via Excel, right? Each record in this Excel spreadsheet equates to a single hex. You have the centroid of the hex, the center point of the hex in coordinates, so you can quickly find where that exists on the map. We have individual rankings of, bedrock, our power ranking, and our national or commercially navigable waterway ranking, as well as our sum ranking, which we symbolized it on in our end result. So you could continue to play with that and munge it from there. Can also be delivered in a portable geodatabase format, geopackage file geodatabase, and that can be visualized in QGIS, any of the Esri tools, or really any geospatial tool or platform that you want to upload that to, for either just visual analysis like we did here, or to take that a step further and continue to iterate and refine and maybe add some more parameters and only analyze them for areas that are in green. What we'd love for you to do, though, is bring your results into the Pivvot platform and use some of those tools that Justin spoke about at the top of the meeting, in coordination with the analysis or the examples that we've just kind of run. So what I've done here is just brought in a piece of that end data set we created, that level 10 data set, into the Pivvot platform. And we can start overlaying it with some of other Pivvot data sets that we didn't necessarily use in our initial analysis. Right here, I've overlaid it with our smart parcel layer, which combines parcels with similarly named owners. So you can kind of, if John Smith owns 4 parcels next to each other, you can kind of see, oh, he owns this whole thing. If we want to talk to him for whatever reason about buying or using his land, it's only one person to contact. But you see here, right in the middle of our screen, Matt Mueller, John owns this parcel. There's some good land in here. You can start to look at the owner name. total land value, all this information in the tax map parcel data that we have, and just continue to iterate and refine the process as you work through your use case. There's also a number of out-of-the-box reports that can be run within the Pivvot tool. Here, just show a snippet of a greater report where we're looking at percent slope or flood frequency for a particular area of interest, and all of the breakdowns of different conditions within that area. So wrapping up here, some takeaways from this. What's most important to your use case? Is it time? Is it budget? We can always run these things faster and in parallel by throwing more horsepower at it. But there are also some decisions that can be made, some considerations like the eliminating states that don't touch commercial navigable waterway. So identifying, what's most important to the process and keeping that in mind as you do your analysis and iteration. Identifying core data sets early in the process, right? If we decided, oh, well, we actually want to throw in a fourth data set to this analysis, that would kick us all the way back to the step before we started to iterate, where we're selecting our parameters and how they interact with each other. So getting those locked in as early as possible, again, is key. And determining the format based on your use case, those analysis units and the size of those units, whether you want the hexes, property parcels, tax map parcels, voting blocks, any other, those aren't the only considerations. There are other ones outside of that. Those are just the ones we gravitate to. And then iterate on your process. After you've iterated and identified the parameters, the data sets, you're ready to scale. And consider the resources, to scale. How fast do we want to run these things? How fast do we want results back? And also just keep in mind, Pivvot can help. We'd love to collaborate with you on any and all of these problems. All right, I'm going to throw it back to Abby for our Q&A session. Thanks, everyone.
Awesome. Thank you so much, John and Justin. We do have a couple questions here, so I'll go ahead and kick us off with our first question, which is, what is a situation where you would use property parcel data instead of hexagons?
Yeah, so like I was showing in that slide, actually, I'll just go back to that slide here. If you have any ownership information that you are concerned with at the early stages of analysis, so maybe size of parcels, you need a certain size of land to build or evaluate whatever you're doing, and you just want to eliminate anything that's under that size. So as an example, maybe this chunk of land up here would meet our conditions, but this small one wouldn't. You could eliminate that at the start. Or if you're concerned with things like land value or other ownership information, maybe government-owned land versus private-owned land, you could use those things. So another way of saying that is anytime there is information embedded within those boundaries, be it property parcel or one of those larger man-made boundaries, it would be a good idea to consider that for your units.
Great, thank you. Okay, another question we have is, how are you able to run this so quickly?
Yeah, so the primary two tools we use for this analysis is FME, an ETL and really good geospatial processing tool put out by Safe Software. And all our data sits in Postgres databases with the PostGIS extension on them. So by indexing our data within those databases in very specific ways that match how we query the data, we are able to access and compare them very rapidly, more so than you would, if you're comparing two shape files, for example. And also the hex units that we selected for this example help greatly, because once you have moved everything into that hex unit, it becomes much easier to compare data set to data set, because you're no longer really doing geospatial analysis as it's traditionally thought of. You're just comparing hexes to hexes. Another thing to keep in mind is when I showed those times, those processing times, like the state of Alabama took about an hour to process. That took even that long because that time includes the conversion of commercially navigable waterways and power lines to hexes. But once I've taken off that byte, once I've converted those to hexes, any iterations at the state level would actually be even faster than that, because I'm no longer doing the conversion to hexes. Things exist in the hex world, and I can just do those comparisons hex to hex. So a number of things stacked on top of each other allow us to get those time savings.
Awesome, thank you. I see one more question here, and we probably have time for a few more if anyone else has any to throw in the Q&A. But our last one that I have here is, how does bringing my own data work?
Sure. So there's a couple, three ways that could be handled. If you are a user of the Pivvot platform, you can upload your data to the system, much like I did here, right? So the hex grid here is not a supported pivot layer, obviously, because we just created it in this example, but I have uploaded it to the Pivvot platform and am viewing it alongside our Pivot parcel data. So you can do that if you are a Pivot user, and we can walk through how to do that with you. If you are not a Pivot platform user but would still like to collaborate with us on this, there's two ways we could handle that. You could either provide your data to us for ingestion into our system, in a secure lockdown, only you're looking at it way, of course. And we could add, all of our magic on top of that to make it perform really quickly in our system and alongside of all of our other data sets. And delivery of that could be any number of ways, whether it's SFTP or handing it off to us through any of the cloud data providers, AWS or Azure or whatever. There's any number of ways to get the data to us, but we can make it work very efficiently with our data sets. You might also, for security reasons or project rule reasons, not be able to share your data. It might be important that it stays on your system. We can work with you in that way as well. We can sort of move our analysis to your system. It's going to be a little bit more heavy lift and heavy integration, of course, but it's something we can do to facilitate that if data needs to stay in your system, right? We can move the engine to you, so to speak.
Okay, thank you, John. I don't see anything else coming through on the Q&A here, and it looks like we are almost right at time. So if neither of you have any other final thoughts, I think we can go ahead and wrap up. Thank you, everybody, for being here today. And if you have any other large-scale data problems or challenges, please reach out to Pivot. We'd love to work with you to solve them. And in case I didn't already say this at the beginning, this webinar will be recorded and shared if you'd like to share with anyone else to watch later. So thanks again. Thanks, Justin and John. And we will go ahead and end now. Thank you.
Thanks, everyone. Thanks,
Thanks,
Abby.
everyone.
Bye-bye.